It's perpetual. So like, until you turn the power off of the VM, it's going to keep happening. There are 4 conditions for deadlock. You have to have, well, I'm not going to get it. I can tell you if you want offline, but the 4 conditions, if you break any one of them, you can prevent deadlock. We're going to look at an example of deadlock coming up here. But here is an example of using futures. Here's another example of using futures. So I've got a future that returns a constant. So how long does it take to return a constant? 0 time. I've got to submit that first one, and then it waits for its result. All right. So the first callable on the executor is a deadlocking callable. Now, what do you think that one does?
Deadlock.
It turns out. Okay, so I put this future on there, and then I wait for the result. So this future gets put on. How long does it take for that to run?
You put it on.
It doesn't take any time to put it on the queue. How long do you think it takes that method called connection to MQ? And it's not going to let go of it until it grabs the database. So thread 1 has a database. Thread 2 has MQ. Deadlock. That's it. You're done. Your system is out. Now, in real terms, let's say you have, how many database connections is a reasonable number of connections? 50? 50, let's say. Okay, how many connections to MQ? 50? Let's say we have 50 of each. All right. Have you ever had a system that had more than 100 simultaneous users?
Sure.
Or actually, in this case, 51 simultaneous users? Realistically, it's hard to get that situation with that number. But if you have a couple hundred simultaneous users, the system only has to run for a while. The potential is there. Now, it turns out that one of the ways to avoid deadlock is if you add a global ordering to the shared resources, and always everyone acquires them in the same global order, you're fine. So if thread 1 tries to grab a database and then grabs MQ, and then thread 2 tries to grab a database, it's not available, so it waits. It'll never grab that second one, and you will avoid deadlock. So one of the simplest ways to avoid deadlock is you apply a global ordering across all the shared resources and make sure that everyone always accesses them in the same order.
Client side.
Client side. But that's a thing. That's one way to avoid deadlock. So that's one solution to this. Here's another solution. This is a situation where, rather than me blocking, I'm going to continually retry. It's a lot more complex, doesn't block, and it just retries over and over again. So here's what happens. There's no future, so I'm going to submit like I did before. Now, is that future done? Well, it can't possibly be done because there's only one thread, right? So I'm going to resubmit myself and then return just an empty string. So what happened is the deadlock got on there first. He put on the return a string. He returns. But as a side effect of him returning, he puts himself back on the queue. The string process runs. The single thread allows the second version of this guy to come back in. Future's not null. Future is done. And if it's not, it would just wait. And so I go through that same thing twice. The first time through, it has a side effect of submitting a new one, just like before, but also it returns, and that's the key. So I end up running the same task multiple times, and eventually that return as string happens. This is much more complex, right? I mean, it works. The other one's guaranteed deadlock. This one actually works. But this is an approach. It's a non-blocking approach.
Wouldn't the first time you return the empty string, wouldn't this future say is done?
No, because that future is actually equal to the return of string. This future, let's see. Notice I'm waiting on actual result down here. I'm not waiting on future. Now it turns out I haven't updated the slide, but I've since rewritten this and I have one future. You can write this with just one future. It's possible. It's a little trickier, but the bottom line is it's pretty close to this. You just don't need 2 variables. But conceptually, never block. If you don't block, it turns out you can't deadlock. But what does that imply? I'm going to retry. Does that sound like anything we talked about earlier today? The check and get, increment and get. I'm going to keep trying to increment it until I successfully increment it. Working on the assumption that I'm not going to do that a lot statistically because I'm not going to have a lot of contention. And so my overall performance is better. But another important side effect is if you don't block, you can't deadlock. I really didn't know that was going to come out my way. I'm enough of a dork. The last thing I need is something like that. My wife would kill me. And rightfully so. So this is an example, and in fact, this kind of thing where I'm a thread, I'm a task, and I try to do something, and if things aren't set up for me to do it, I just put myself later on, and I keep putting myself later on. Oh, now I'm done, I can finish. That's actually a style of writing tasks, and if you don't block, your system is going to... What you're really doing is you're avoiding deadlock at the possible expense of busy wait loops, which means your CPU usage might go up, but you don't deadlock. And also, as long as contention is relatively low, then you don't even really have a problem with CPU utilization because you're not busy waiting a lot. What's wrong, Barrett?
You can confuse me.
Okay. I'd like to think if he accentuated the confusion within.
He very well might have. I can neither confirm nor deny.
Okay, now, I didn't say this before, but when I had that server, and that server was both responsible for connecting clients and processing the clients, that's a violation of a principle from, turns out, among other places, this book. Who's heard of the solid principles? Okay, there's design principles, solid. S, single responsibility. A class should have a single responsibility. O, open-close principle. L, Liskov substitution principle. I is interface segregation. And then D is, what the hell's D? The second D is law of Demeter. What's the first D? Oh, dependency inversion. All right? But single responsibility would suggest that something like a server class being both responsible for connecting to the client and processing the client request is maybe a bad idea. Notice we separated it out. The server created a thread that processed it, so we actually separated that into two separate responsibilities. Well, this is pretty complex. Actually, if you look at this, it turns out this is a little finite state machine. The first state is, I've never created a future. That immediately puts me into state 2. State 2 is either going to be ready or not ready. The first time through it's not ready. The second time through it probably is ready. Well, how many of you have heard of the state pattern? Well, 4 or 5. One of the things you do in the state pattern is the different states are represented as separate objects. So a logical extension to this is to break the part of it up into 2 pieces. One of them puts the task on, and the next one sits there and waits. And that's another extension to this. Huh? Oh, is that? I don't know. Well, there's no picture. Let's see. I'll hit the X button. Come on in.
No microphone on the X.
I like talking to myself. Don't you do that? Okay. So that's just, that's the next logical step would be to, well, acknowledge the fact that I have a bunch of smaller tasks and break them up into smaller tasks. Notice it gets rid of the null check here because I know this is the first one. It doesn't need to check the state because it knows the state is the future's never been signed. And then down here, it just somewhat simplifies the code. Well, maybe it makes it more complex. Each piece is a little simpler, but the overall thing might be more complex. Questions about that? Your brain's getting full? Getting there? Getting there? All right. Let's. I'm just going to go through a litany of some of the other classes and talk about some of the other stuff that's in Java 5 that's available for you now. And we'll wrap up. Notice, what time? We don't want to finish at 8:30, right?
Sure, 8:40.
8:40? Okay, so I'll just go through a quick litany. These are things that you might want to be aware of. Concurrent hash map. That's actually, a version of concurrent hash map has been around for quite some time. We decided it was 2002, maybe 3. Something like that. It wasn't 92 or 93. It was 10 years after that. It wasn't several years before Java was created. The concurrent hash map is, if you're using Java 1.5, it's in java.util.concurrent. If you're using Java 1.4, you can get a version of it from the Oswego. So if you look up OSWEGO, you can get the Oswego concurrent collections. And in fact, those work in 1.3. I'm sure they work in, I think they work in 1.2, but they certainly work in 1.3 and above. They work in 1.2. I know that because, in fact, at my previous consulting assignment, we went from Java 1.2 to 1.4. We skipped 1.3, and we've been using it for some time. So,
do you know what Oswego is? It's a school somewhere.
It's a school somewhere, yeah.
In New York.
Which one?
It's in New York.
That's the name of it? Is Oswego, or is that an abbreviation?
It's like U of
It's an
I.
acronym.
Yeah, it's like U of I or something like that. Which, if you're from Illinois, that's University of Illinois, Champaign or Banff. From Iowa, it's University of Iowa. Go Hawks. Anyway, concurrent hash map is a thread-safe map. It has some advanced methods that the regular hash map doesn't have, like set if the value is already this value. So I want to replace it if the value is what I expect it to be. What they do with the concurrent hash map is, where a hash map uses one lock for the entire set of buckets, a concurrent hash map uses 16. Now, underneath the covers, it's more complex. It uses more memory. But it is possible that you can support simultaneous reads and writes, multiple reads and multiple writes to a concurrent hash map. I'm not sure about that, actually. Simultaneous writes, yes. Simultaneous reads, yes. I'm not sure about the two together. Because underneath the covers, they've taken and said, well, rather than having one lock for everything, I'm going to have 16 locks.
It depends on if your data is in different buckets, right?
Well, and that's an excellent observation for us. If you have a bad hash function, that's basically,
Return one.
well, yeah, return one is a really bad hash function. That turns your hash map into a linked list. And well, the great thing is that you'll never get more buckets. But you've just taken let's see, a constant lookup and turned it into order log big O n. That's not so good. But if you have a hash function that actually distributes things well through the buckets, then it's very likely that oftentimes you will not have any contention, and as a result of a lack of contention, your overall performance will be better. You can use this now. It's going to be a little more memory, a bit of a memory hog than a hash map, but it's going to perform better. And it's one of those things where a concurrent hash map is just a hash map, or it's just a map, actually. So you can use it, no one will know you're using it, and it's going to perform better, and it happens to work better in a multi-threaded situation. And so it's one of those sort of free efficiency gains, right? One of those free efficiency gains. Just like using the atomic variable is sort of a free thing. All right.
So if you use atomic concurrent hash map,
Well, I could use an atomic reference on a hash map. That would be pretty crazy, though, on a concurrent hash map. I wouldn't do that. Definitely wouldn't do that. I'm going to skip down here for a second. Semaphore, there's actually a class now called Semaphore. A semaphore, for those of you who know about semaphores, P and V, ever hear of those?
Yeah, right there on the slide.
Remind me, is V get and P put? No, actually, P and V are the operators, the methods on a semaphore. The guy who came up with them was Dutch. And I don't know what they actually stand for, but I always thought it, because it's Dutch, I thought it was P as put and V as get, or something like that. But one of them actually requests one of the semaphores, and one of them actually, yeah, it's not that good. One of them actually requests, and one of them actually puts back a number. So basically, so I can create a semaphore, and when I create a semaphore, I can say, hey, semaphore, you have 5 for a number. And what that semaphore will do is, as long as everyone uses a semaphore, right before they go into a critical section, they try to acquire a lock from the semaphore. The count gets put down by 1. When the count goes to 0, people start to block. And then when I release, someone else gets through. So semaphore is a way to guarantee a fixed number of things, threads, accessing, say, a critical section. Typically, you use binary semaphores, but not necessarily. I'm going to mention lock here. Now, a lock is a heck of a lot like your intrinsic locks, with one key difference. An intrinsic lock is connected to the block that it applies to. Open curly brace, close curly brace. You get to the open curly brace, if you're in it, you got the lock, you're out of it, you're released the lock. With the lock, I lock it in one place, I acquire it, and then I release it somewhere else. So if you wanted to start a lock in the middle of one method and release it in the middle of another method, which is for advanced people only. There are some algorithms that I've got several books. I've got a book of algorithms. I've got several books of algorithms, and some of them are written using semaphores, and the way they're coded, they're broken across multiple functions. And if you actually want to use one of these algorithms, and it's written that way, I mean, if you know it works,
Yeah.
might as well use it, but trying to convert something that locks in one method and releases in another method, it's not semantically possible to do that in Java, unless you use the lock. You can't do it with the intrinsic locks. So for advanced users, danger Will Robinson, for advanced users, this is something that's good. Let me tell you, when I took my class, a long time ago, when I was doing the multi-threaded stuff, I had no end of frustration with semaphores and locking. It was always a lot of suffering. So I would encourage you, if you study those three problems, producer, consumer, readers, writers, and dying philosophers, if you read those, experiment with them for a while, but then you can find solutions to those on Wikipedia, all right? Or you can get an algorithms book. Huh? What?
So reading the solution on Wikipedia is after you've written your own, right?
Well, you try to solve it yourself, and then you look at the solution there, right? But the bottom line is, if you can identify that my situation is like readers, writers, or is like dying philosophers, then you can use these solutions to solve the problem. And if you have it in an algorithms book, something like lock and semaphore will allow you to directly implement the solution. Even if you don't understand it, you might be able to solve a problem that's a tough one to solve. If you're able to solve the problem and it's semantically correct, and you don't quite understand how you solved it, but you're basing it on an algorithm out of a book, I don't find that to be too bad. Sometimes that's what you got to do. Just two other things: barriers and latches. A latch is something that it's sort of like weight. Like, let's say I want to do something. I want to try 5 different algorithms, and I want to give them sort of a fair starting point. So I start the latch off with a count of 5. 1 thread tries to go to it, nothing happens. 2 try to go through. 3, 4. As soon as the 5th one hits, the latch opens up, stays open forever, and those 5 are now free to possibly in time. So they block until the latch opens, and then anyone else that waits on the latch gets through. So a latch, once open, lets people through. So for example, if I'm in a test and I want sort of all these different threads to start about the same time, or at least have a fair chance of starting at the same time, I might use a latch. All right? A barrier is sort of something, it's sort of like a latch, but you can reuse it for one thing. So a barrier will open up, and then it can close again, and open up and close. Situations where, for example, I want to go out and compute, like, remember the game of life? You ever seen the game of life? So let's just say that I think I can actually get something out of it. I'm on a multiprocessor machine. So I'm going to break it up into a grid of 4, and I want to have those 4 things go out. And when they join back, I'll redraw the next screen, and then have the 4 things go out, calculate, come back. So you parallelize a big data set. You go out, you calculate the next version. Actually, if you're doing like double buffering on graphics stuff, oftentimes what you'll do is you'll do something like that. You'll have multiple threads, calculate the next screen, and then you'll switch to the next screen. Then you'll calculate this screen back and forth. And so a barrier might be something you use to implement that kind of an algorithm. Underneath the covers, I'm pretty certain barrier, latch, semaphore, and lock are all using this non-blocking opcode to implement them. So they're actually pretty efficient. All right, that was sort of, in a nutshell, some of the new stuff in Java 5, and also some basic threading stuff. Well, basic concurrency stuff. I would consider all the material that I talked about maybe at most intermediate. And the reason I would is, if you're doing multi-threading, other than, say, knowing some of these classes, you really need to know everything else. So multi-threading is definitely the reason there's so many containers out there that try to take care of the threads. Designing something with multiple threads isn't always faster, but it can be substantially faster. It is almost never easier. Sometimes some algorithms actually lead themselves to a better understanding in a multi-threaded solution, but most of the time it's harder. But if you are careful and you can do stuff correctly, you can get some pretty amazing performance gains when you're I/O bound. unless you have a multi-core system, and pretty much everyone's almost going to have a multi-core system. If you don't already have a multi-core on your phone, you should feel lacking. No. You joke. What do you think? 3-4 years from now,
Yeah.
multi-core?
Yeah.
Absolutely. I'll bet you. They can fit something like, if you take an 8186 and you put it on the die of an 8386, you can put 1,000. 8186 is on the die of a 8386. It's a lot of processing power. So I want a 1,000-core 8386 where I'm having the black burn mark on my hand because I'll be able to read my email faster than you.
I can't read your email like that.
Well, see, so I guess it's already working.
It's a mutex.
Yeah. So, any questions about the Java 5 stuff? Threading? I mean, there's sort of a spattering of stuff. Most of this material I would have covered in a three-day course with lots and lots of time. The actual, I think I mentioned the course time is like 70% realistically. They're sitting there, 30% talking and discussion.
I have a question. When you say I/O bound can usually be solved with, adding concurrency, the only thing I can think of where that maybe not applies is file I/O. Is that correct?
File I/O is very slow.
Because if you're knocking on one file system,
that's a good point. And in fact, in general, you can generalize that for us. If you and I are trying to access the same record in the database or access the same resource across MQ, then really you're not going to gain. So presumably I'm working on different things, but I'm I/O bound. So a condition to I/O bound is that you're also not trying to modify the same conceptual thing. No?
I was just going to say we memory map files usually, so that goes away.
That's the
Sucks
NIO
all
stuff.
thing in.
Yeah. Java native I/O.
And also, you said it's always bad to put all of your code in a servlet. Can you explain?
Absolutely.
Single responsibility.
I think it's always bad because in general, as a general principle, and I believe this before servlets existed, I try not to put my business-specific stuff in enabling technologies. That includes servlets, that includes EJBs, or any kind of applets. Enabling technology is enabling technology. Don't rely on it to actually host your stuff. It's pretty common that people will put in their forms, like I don't know, maybe this is Windows, but I think it happens in Java as well. You have these huge VB forms that have all this business logic. The only way you can test that is to have the GUI active. Well, it turns out that's a lot slower than, say, if you just taken and separated it, GUI stuff, which any kind of complex interface, there's enough complexity in enabling and disabling stuff that you don't need to put your business logic in the same place. So by separating it out, it makes this testable, and it also makes it fake-outable, test-doubleable, mockable. So I think putting something in the same place in enabling technology is always a problem because of the square law of computation. Remember that one? The square law of computation is a principle from general systems thinking. So it applies to systems, not specific anything. And the square law of computation says the complexity to solve a problem will grow at least as fast as the square of the number of things that are simultaneously interacting. So if I put two things in one place, it'll be 4 times as complex as 2 things that are 1 complex. And typically, we don't just do that. I mean, I've seen things where I've got the GUI, I've got database access, I've got other external resource access, and I've got business logic of different kinds all in one place. And then you get methods that are 2,000, 3,000, 4,000 lines long. That code that I told you about that took 26 hours to run, it was a 1,200 line method with 8 to 10 levels of nesting repeated in other places. My end solution, counting all, that was 800 semicolons, or 1,200 semicolons. My solution was 400 text lines and ran 97% faster. And it had nothing to do with, I mean, the code was just terribly written. I mean, it used a switch statement with conditionals inside the switch statement. And then if you looked, this code, in this case, well, this is the same set of cases, just later on, same if. It was just cut and paste.
With the code fix that wasn't in the other copy paste.
Well, I mean, the code worked. It took 26 hours, but it worked. So, you put something in the same place, and then it's hard to know the structure, and so it's hard to make improvements. So I think it is, I'm going to go with that. In fact, if remember there's 3 levels of never. let's go with the 3 levels of always. I'm going to go for a triple always. No, I'll put that as a double always. I mean, I can concede that there are rare circumstances where you're working on your phone that has a limited amount of memory, and adding an extra 6 bytes is going to actually make a difference between the system working or not. So in a situation like that is pretty hypothetical, yeah, it might be better. But so I'll give it a double always.
I like to request that you close with a joke about dining philosophers and starvation.
Not have any.
Yeah.
The dining philosophy, like I'll give you the setup though. Here's the problem. You've got n philosophers, say 4 philosophers. And you've got, in the classic problem, I think it's chopsticks, but I've always seen it as forks, and there's 4 forks. For a philosopher to eat, the philosopher has to have 2 forks. All right, so all the philosophers try to grab forks. One grabs from the right, the other one grabs from the left, one grabs from the right. Well, if that happens, and I get them both, I eat. But once I grab a fork as a philosopher, I will not let go of this fork. It's not preemptible until I eat. Here's the problem. They're around a table. So I grab with the left and then the right. Well, it turns out that at some point you get a circular dependency because someone's left is actually someone else's right. And so what will happen with dining philosophers, you run it. And this actually, it's pretty easy to set this up. If you set that problem up, it's very easy to get deadlock. You'll get deadlock after not too long. And by deadlock, I'll have a fork, everyone else will have a fork, and no one will get eaten. And there are lots of solutions to dining philosophers. One solution is you add a fork. If you add a single fork, then you're guaranteed you can get rid of deadlock.
Get rid of selfish philosophy.
Yeah, get rid of selfish philosophers. So what happens is you retry. So I grab a fork, and if I can't grab the other fork, I put it back down. What happens with a retry logic, if you have a lot of contention, which in dining philosophers you do, you find a lot of CPU utilization, but not a lot of you can not a lot of eating. You can order the forks, and what happens? You take one philosopher. Most philosophers are left-right, but one philosopher is right-left. And that breaks the circular. That's equivalent to a global ordering. Another thing is you put all the forks in the middle. And then it's a pool. But then you still have to worry about, I could still get the situation where all the forks are in the pool, every philosopher gets one. Yeah. And so you still have, there are ways to solve that. And actually, there's a good solution on Wikipedia that does basically that.
They're philosophers.
You know, one of the ways you solve the deadlock is you don't synchronize any resources. If you don't synchronize, you don't lock, you're not going to get deadlocked. What that means, though, is you've got 2 philosophers both using the same fork. So I'm not sure how that would exactly work.
I think if you don't block, you can't deadlock. Is the quote immortalized?
If you don't block, you can't deadlock.
Yeah. It's got the rhythm to it.
Yeah,
Gotta get that.
It has right numbers going. Yes. Other questions, guys? I hope this was technical enough for you. Was that technical enough for you?
It's not a question. Do we have any patterns that are specifically associated to the threading programming? If like we are working in applet, servlet, this, that, and all.
Well, okay. So in servlets, the pattern is don't share. So you don't actually everyone has their own copy, and by not sharing, you effectively are multi-thread safe. Right? You're told don't. You like that? Don't put anything in servlets. Everything on servlets are passed on the stack. And by the way, a fact that you may or may not know, every thread has its own stack. And so by doing that, you effectively have no shared information. So you don't put any kind of attributes in a servlet. I mean, that's one of those nevers because it's safe to put an it's safe to put an attribute in a servlet if the information is not specific to any particular caller, like some kind of cache. You don't generally see people doing that, and I wouldn't recommend doing it, but technically you can do it. All right. So for servlets and EJBs, the idea is you don't do threading yourself. You let the container take care of threading, and then it'll share data. And if you have contention, say, in the database, you set your isolation level so it doesn't happen, or you add in variables. Like the Hibernate. How many of you have used Hibernate? Hibernate can actually take care of versioning for you. And so what will happen is
if you let it.
If you let it. Yes, you can constrain Hibernate so it can't do anything. I mentioned those 3 problems, right? And then you saw some other examples here, not blocking or and so on. I'm sure there are others. And if you look at actually the book Concurrent Programming, what the hell's it called? Concurrent Programming in Java. Yeah. I think that's it. It's a really good book, and it actually talks about a lot of patterns. I can recommend that book, Mina. So, other questions?
Is that legally blonde up there in the upper left?
Yeah, what's on there?
That is legally blonde. Apparently, I have a couple of individual tracks that come off of different things. So yeah.
You just went
Like the Kelly Clarkson album?
No, I have the whole album.
Let's not.
I've also got
And a lot of Morrissey.
that's actually because of my wife. I like Morrissey, but she loves him. This is all going on YouTube,
Yeah,
right?
you're definitely.
Great. That's just great.
Have you ever used the work manager API?
I have not used the Work Manager API.
And there's two that I've heard of. IBM came out with one, and then there's the JCA version.
I haven't used either one of them. I'm thinking that they're similar to the Executor, probably a little more
Does
sophisticated.
the executor it does callbacks?
It doesn't actually do callbacks, but with futures you can get polls. I mean, not pushes. But I have. Is that what those frameworks look like? They're callback based.
Yeah.
No, yeah. I haven't used them. And also there's the swing the swing main thread, whatever it's called. Right? Swing is single threaded. Most GUIs are single threaded because they're hard to do correctly. And so you have like invoke later, so that your GUI is responsive and so on. Well, okay. So how's about we stop, and if you want to continue asking questions, people who want to get their book can get their book. All right? And I'll stay around for a while.
Correct? Everyone in here that wants
A chance?
a chance to win?
Single-threaded ticketing one.
904.
How come we don't have two numbers?
Either book, hardback, softback, both autographs. This was a little newer, this was a little older, but this was anyway. I'm not. They're both. They're both. There you go. Yeah, you get, if you win twice, then we lose you. 903. Are you serious? This is 903.
All right, these are.
There you go.
Do you always win?
Did you win at lunchtime?
But I didn't win it under lunchtime.
I think that's all we've got. Thank you, Brett.
You're welcome.
Good presentation.
I'll hang around for other questions.
Everybody hire Objectmentor.
Sure, why not? I'd love to do some work in my home city.
See you.